Right, this is my solution to Walter Lewin's problem 189, and it concerns at its heart field energy density. Okay, we have two plates. I'll represent them with these two discs. The shape doesn't matter, it's the area that matters, but they must be the same shape so they can line up. Right, they're a distance x apart and they have an area A, and we move them slightly. Initially we have a situation where the top plate is charged positively, the bottom plate is charged negatively. Now, just to be clear, because of the gap, the pluses are here. They're actually on the inside in each case. Bad drawing, but I didn't really have the space to put them in. Okay, that sets up the situation. And it's important to note that there's no field outside, and I'll just briefly explain what's going on there. If we have a bigger separation, where the dimension of the plate is clearly not a lot greater than the separation, what happens is we get our field lines. Again, we've got our charges here and here, and a little bit of charge is now on the other side of the plate, because although the majority of the field lines are coming down, they start to bow out, and you can see this. I've shown it here. There are more. It's just a representation, but essentially this is what we have. So the larger that gap gets, the more the field expands, and the smaller the gap, the more the field kind of moves in and is concentrated between the two plates. So in this situation, the volume of the field would be extremely difficult to calculate. However, if we go back to our initial problem, because we've made the gap very small, we say that to an incredibly good approximation, the field is totally contained within the plates, the two plates, and so calculating the energy, the total energy of the field, becomes very easy, because the volume enclosed by the two plates is very easy to calculate, and that's at the heart of the problem. So, right, in Walter Lewin's lecture 7 of 802, he shows that the field energy density is given by this equation, a half epsilon naught E squared, and everywhere I am taking the permittivity to be that of free space. We're not dealing with dielectrics in this situation. Also, from previous lectures, we have the definition of charge density, the surface charge density, as being the total charge on the plate divided by the area. That makes reasonable sense. And also from Gauss's law, we get that E, the electric field, is sigma, which is the charge density, divided by epsilon naught. So eliminating the variables that we don't know, E and sigma, we can see that the field energy density is 1 over 2 epsilon naught Q over A all squared, and that's per unit volume. Okay. So, sorry about that. So we can easily calculate the initial energy of the field. The volume is this very nicely defined cylinder, AX, A times X. So initial energy is the field energy density times the volume, which gives us this, which gives us Q squared X over 2 epsilon naught A. And similarly, the final energy of the system, we've just increased the x, is Q squared 2x over 2 epsilon naught A, which turns out to be twice the initial initial energy. And I'm not sure if I said this already, because it's a conservative field, it's actually path independent. All that matters is the starting point and the finishing point. If we went round here, the field would simply adapt, and when we go to 2x we get the same answer. That's because it is a conservative field. In this case though, we're just going to move it slightly, but useful to note maybe. Okay, so we can straight away solve the third and fourth parts of the problem. We can see that the change in energy of the system is final minus initial, because we have conservation of energy, and that's q squared x over 2 epsilon naught a, which is equal to the work done by Walter Lewin. The energy's got to come from somewhere, and only Walter Lewin on this occasion is going to provide it. So they're the same thing. Work done by Walter Lewin is the same as the change in energy, and he's had to do work. The energy has increased, so he's had to put work in, q squared x over 2 epsilon naught a. Right. The force, jumping back, the force between the plates we can get from the energy again. If we consider our two plates and move them a tiny bit, a delta x, we have increased the volume a slight amount, so we've changed the energy of the field, and we've also done some work. We know force times distance, so the work done is force times delta x, which is equal to, because we have a conservative system, the change in energy delta u, or in this case u final minus u initial. And if we put this in, here is our final energy minus the initial energy, we get the work done is q squared delta x over 2 epsilon naught a. Hence, if we simply divide out our delta x's, we get that the force equals q squared over 2 epsilon naught a, and also that's the force holding the two plates, that the two plates are exerting on each other. We're assuming something is holding them there that does not interfere dielectrically with the field, and so to move them apart, Walter Lewin needs to provide something slightly more than the force F to move them apart. And that, I think, well, not quite. That answers the question. One last little bit. I could have calculated the work done earlier on, rather than just taking final minus initial. I could have said, having worked out what the force is, we could have done the integral of force times integral of force with respect to x, and we would have got the same answer, q squared x over 2 epsilon naught a. This is more the sort of technique you would use if you were faced with something like, say, a cylindrical system or spherical symmetry, where you would have to do an integral because the a effectively is a function of x, or it would be a function of r in the case of cylindrical and spherical symmetry. And that is all I need to say. Thank you.